speaking here. This is my first time in South America, so this is particularly exciting. I'd like to share a story that happened to me that kind of speaks to the bigger picture of entrepreneurship and innovation. It was an opportunity that landed in my lap, only I didn't see it at the time. What had happened was that I tore a ligament in my wrist. That was excruciatingly painful, but once the pain went down, it was obvious this was a great opportunity because I'd been meaning to do some explorations with 3D printing and medicine of this type for a long time, but it's very expensive and illegal and dangerous to do your testing with live human subjects, unless the subject is yourself. So I got very lucky. I guess unless the subject is yourself or your spouse, depending on the nature of your relationship, but that's up to you too. So I looked at what my chances are with the doctor, and he said, I've been facing surgery followed by 4 months of this. And that's miserable. And I decided, okay, there's where the opportunity lies. Is this cast, the common cast, is it what it is because it's the best possible solution to the problem, which is simply to stabilize this part of your body relative to this one? Or is it that nobody thought to rethink it? Nobody got around to using all the new tools in our toolbox to come up with a better solution. And sometimes that's really the nature of innovation and design, is using your new tools to rethink the question from the start. So we did exactly that. Now, I was the design director of 3D Systems at the time, so I had access to people and technology and tools and skills. So we decided, let's just hack the system and start over. So the first thing we did, I wanted to find out what was going on my wrist. So we took the CAT scan data and we 3D printed it. So now I could hold in my hand a one-to-one example, a roadmap essentially of what's happening inside my wrist. We then put my arm in a 3D scanner. This is one that was invented by my team at 3D Systems. And we took an outside scan of the shape of my arm. We used that shape then to map against it where the bones are, the blood flow, the tendons, the nerve endings, all the stuff that we had to keep away from. And then we started designing using a three-dimensional force feedback tool, also designed by my team at 3D Systems. And this is a sculpting tool where we can sculpt in space with feeling the physical force feedback. We designed a cast very unlike the traditional cast. The idea was to say, well, really all you need to do is stop motion here against motion here. So we did that. We called it the bikini because it covered the important stuff and absolutely nothing more. So I took this concept to my doctor and I showed him and he said, interesting, whatever you do, do not use this. This is an experiment. You might ruin your arm for good. Do not try this. And so I said, great. And 3 days after the surgery, I cut off his cast and I put on my own. That's also the nature of a hacker. And it turns out that I was able to then put on hot and cold pads directly on the surgical site, starting a few days after the surgery. Well, you can't do that if you're all wrapped up. I was able to get acupuncture done on the surgical site, and it reduced the pain and the swelling. I was able to massage the scar tissue out. I was able to get sunlight on the skin. I was able to take a shower every day, as well as to scuba dive and swim. And then the doctor visits. Well, you look at this and you say, that's an $800 cast that's 3D printed, compared to a $30 cast that's made the traditional way. How do the numbers work? Well, it turns out that medical numbers are different because my doctor visit was a matter of walking into the office, rolling up my sleeve, taking a look, and then walking out. A 10-minute visit, what would normally be an hour-and-a-half visit. So the time saved paid for the cost difference in the parts many times over. So we took a look at what this might look like in the future, and we said, well, how about something like this, where you print directly on the skin with room temperature printing, non-Cartesian printing. And this was our fantasy concept idea. It turns out there are groups working on exactly this. So this is what we might see looking into the future. So 3D printing was never about this kind of thing in the beginning. It was never about medicine or solving problems in these interesting ways. It had one goal. It was a guy named Chuck Hull, 35 years ago, who left MIT and decided that there was a challenge that the US was facing, and that Japan was killing the United States in the ability to make better cars. That was before today, when pretty much everyone in the world is doing that. But then Japan was the only one we were worried about. So he pegged it that the long lead time item, if you could shorten the time to market, you could improve competitiveness. So he designed a machine that would create 3D printed dashboards. That was the only thing he wanted to do, make dashboards faster. Simple. Well, he was building off of what we call Industry 2.0, and that is the assembly line, it's mass production, and what he did is he added a couple ingredients that accelerated things a little bit forward, and he added these two ingredients, the ability to make complexity at no burden to the system, and the ability to have a rapid development cycle to speed up the whole process. And he did that by creating an all-digital workflow. And so what he didn't realize is that when he opened those doors, all of a sudden, everything else came along for the ride. Some of these things had been around for a long time, data visualization, optimization, things like that. But others couldn't have existed before, like that one down in the corner, faxing parts. Faxing parts? That's, again, 3D printing only. So now you look at how things are made. Well, rapid development cycle, low quantity manufacturing, part consolidation, and you get the modern way you prototype a car. It's not just the dashboard, it's the whole car. You've got the rubber parts, you've got the metal parts in the engine and the manifolds, you've got the plastic parts, you've got down to the optically clear headlights. Everything about the car is 3D printed before it's happening. Now that is just building off of what he started, which is accelerated prototyping. Where things are going today and moving into the future is a little more exciting than that. Bugatti has suggested this with their 3D printed wheels. Now, Bugatti is doing this for a very good reason. They are able to make shapes that have never been able to be made before, so they can make these really cool patterns. And they can get time to market very fast. But also, they have an all-digital inventory now. That's a big, big deal. Because if you can have all of your parts as ones and zeros, then you don't have to keep vast warehouses of all of your backlog ready for your next generation cars. All you have to do is pull down some digital files and print them. And so Mercedes is doing this now. They're in the game. They're keeping old cars alive by 3D printing all the parts to keep them alive. And it's not just cars. It's things like tractors. It's the humble washing machine. This is the way manufacturing all across the board is going. And there's a growth industry here because 3D printing your parts takes care of some of the challenges you have with inventory, mainly the unpredictable nature of it that's inherent to it. And so companies like this one, spareparts3d.com, well, that's what they're all about, is filling that void. And this is also contributing to now an 80% growth in metal printing. 80% growth in 2 years. That's exceptional. Very few industries grow at that pace, but everybody now wants to print metal parts. So we're seeing an explosion in that area. So now we can take rapid development cycle. Now, everybody benefits from that. Whether you're making a dishwasher or a car or an airplane, you all benefit from rapid development cycle. We call it shots on goal. How fast it takes you to try an idea, fail, learn, try again. The iterative cycle. The faster you do that, the better your overall product, and the more successful you have. Well, few industries are as reliant on this as Formula One, of all things. Now, Formula One has very complex shapes. They don't use their cars very many times. But here's a catch. The way they used to design the parts, these cars, is designer would design a part, send it to the machine shop downstairs. These guys would take days or sometimes weeks to hand carve or machine that simple part. Then they take it to the wind tunnel, do their testing, take the data, give it back to that designer. Well, now it's totally different. They work in 24-hour shifts now. So the first 8-hour shift designs the part. The second 8-hour shift prints the part. The third 8-hour shift does the wind tunnel testing. And by the time the same designer goes to work the next day, they have all the data they need to modify and create the next iteration. So this also speaks to the nature of disruptive technologies, because if you are a Formula One company, or for that matter, a washing machine manufacturer, it doesn't make a whole lot of difference in this case. And you decide, well, this is a technology that's a little bit alien, unfamiliar, a little weird. We're just going to sit this one out. You probably don't have a chance. Any company doing Formula One, for example, if they didn't embrace 3D printing wholeheartedly, they don't exist anymore. And that's kind of the nature of it. The same thing happened in the hearing aid industry, when in 1999, 3D printed hearing aids were 0% market penetration. 2 years later, in 2001, 99% market domination. So anyone who didn't jump into that game doesn't exist anymore. That's the nature of disruptive technologies. So another benefit isn't just in the speed, but if you can create complex stuff, you can solve a lot of problems that have traditionally been a part of manufacturing. Anyone in this room who's ever had a Ducati, like I have, you know that this is the way you spend your Saturdays, looking at this. Well, that's because complex things like engines are just a lot of parts. We accept that. What we don't consider, though, is that parts are a nightmare. Parts are exactly what you don't want. This is what comes along with parts. We just haven't really figured out a better solution, so we don't really think of it as the nightmare that it is. But it comes along with it. Cost of tooling, complex inventory, added weight, points of failure. If you attach two things, they can break. Process burden, increased size, all these headaches come with it. So if instead of taking all of those parts and bolting them and welding them and gluing them together, you simply 3D print one complex part that has all of your functionality into it, well, that part might be more expensive, but in the long run, it's a lot cheaper. So we're seeing complex things like engines and manifolds and all kinds of parts now being integrated in ways that were never before possible until you could actually simply use an all-digital workflow and go from your design into your final part. Well, now the complexity gives you another little quick dividend. Remember those wheels that Bugatti is offering? Well, it's not just the wheels that are benefiting. The tires are benefiting. And yeah, you'll never 3D print a tire. There's just no point, and it'll never happen. But tires are injection molded, and all of a sudden you can 3D print your injection molding tool. Well, the tools now, because you can print anything of any complexity, that tool can be far more complex than previous, which means your tire becomes a rolling water pump, which means that you'll have better road adhesion than ever before. So this is now going to be the state of the art. Now, while you're printing your tires and all this stuff, why not just print the entire car? That's a question that was asked by Local Motors. They're doing just that. They're looking at doing entirely 3D printed cars. Now, what goes along with that, compared to the old days of General Motors, where it takes something like around $1 billion to create a car, 2 years, and they have to sell 100,000 units to break even, these guys can make very small batch runs. They can make them in the size of states, neighborhoods even, and it's an all-digital inventory. So they have a very streamlined process. They're already making the Ollie, a digital self-driving vehicle. And again, they can make these in very small runs for certain countries and their specific needs. So what does the car of the future look like? Well, part integration, part consolidation, highly optimized structures. Who knows? This is a concept car, but the car of the future is going to be very, very different from the car of today, owing to the advents of 3D printing. So where's this all taking us and where's it all leading? It's pointing to something that we like to call Industry 4.0. And that is taking where we left off with the mass production, but it's adding things like the intelligence of cyber-physical systems. And it looks something like this. There we go. That you can, the laser will then 3D print your parts. They're all done robotically. So the robot, right there in the assembly line, prints your parts just in time, preps the parts, take care of all of your post operations, and then can assemble it right into your assembly line in real time. So no more having your fabrication over here, your manufacturing over here, and your assembly line here. They're all integrated. And if you need more throughput, you simply throw more robots in the assembly line. That's a complete change in the concept of mass production. Now, not only that, you throw a 3D scanner on one of those robots, and now the robot can scan each part as it comes off to make sure that it's perfect. That's traditionally also not possible. And it can compare that against the three-dimensional CAD data so that it knows that either it can reject the part, keep the part, or change the very next part that gets manufactured. So it's an autonomous system that is making its own decisions. That is one of the components of Industry 4.0. Now, what are we seeing in this? We're going to be seeing shoes, for example. 100,000 of these shoes will be printed, but everybody's getting into the game. Nikes, Adidas, Under Armour, New Balance, they're all getting into the game. Now, this shoe in particular, it has 20,000 internal struts here. One of the purposes is that that means that anywhere in the shoe, anywhere in the sole, you have individual physical characteristics. Not possible with traditional manufacturing. But what they're really steering towards is the day when each person will have individual shoes printed for them based on their needs, their lifestyle, their fashion tastes, their sports, their activities. Your shoe will be printed for you, for your own body, based on your own body. Well, that's already being done for pro athletes. They've been doing this for quite a while. And when you're talking about the kind of numbers that shoes are, that's many millions. Well, that's already being done. Invisalign, which is replacing braces in many opportunities, they print 17.8 million of these per year in a lights-out factory, no humans involved. So this is already happening. It's already state-of-the-art. So you throw in something called biomimicry, which is the idea that we can tap into the creativity of nature to solve some of our problems and to address some of the challenges that we face and optimize there. And all of a sudden, we can do something that we couldn't do before, which is optimize things better. See, humans are awful at optimizing. We're limited by our imaginations, by the means of construction, means of fabrication. We just have never had the tools to optimize very well. But nature, which is really just a very, very good 3D printer, well, nature's good at this. So we can start learning from it. Well, now that we have new tools that are more flexible, we can start designing things in entirely new ways. We can design them in optimal ways, like never before, and we can start seeing some of the benefits of this. So nobody loves this better than the aircraft industry, because they live for strength to weight ratios. And reducing points of failure, because failure on an airplane is bad. And time to market, reducing fuel costs, operating costs, everything else. Well, they are going through and 3D printing lots of their parts now. The plane I flew here on, the Airbus A320, has 1,000 3D printed parts. The Boeing 787 has about 1,000 as well. That saves them $2 to $3 million per plane per year. And by printing the dividers that divide first class from second class from the cabin, they 3D print those now in the Airbus A320. They save 300,000 metric tons of carbon dioxide per year, just with that one innovation. And inside the engines, they're 3D printing the fuel injectors. And by doing that, they're able to get a 15% fuel economy increase. That never happens. These are companies that celebrate when they can get 1% increase. All of a sudden, overnight, they're getting 15% fuel efficiency increase. So that's the kind of thing that happens with disruptive 3D printing. So same thing again, back to Formula One, highly optimized parts. We're seeing this in all kinds of industries. So when you talk about optimization, well, what's it really like? My team was asked to do a demonstration part for the Cooper Hewitt Museum in New York of take a familiar object and show us what it would be like if you optimize it, if you treat it in the ways of modern tools, kind of the way nature would. So we took a skateboard, and we entered all the data into the computer, and we let the computer design the skateboard. And it designed it as if 30 million years of evolution had designed it, as if nature was excited to go designing a skateboard. And this is what came out. We 3D printed it. That was a big printer that we had. So we printed the skateboard, and you can see, if you look carefully, 3D printed titanium trucks nearby, and took it for a ride. And perhaps it's the strongest, most improved strength-to-weight ratio skateboard ever made. I don't know. There's not a lot of benefit in that with a skateboard, but it does prove the point. What I find interesting is, though, the higher tech we get, and the more sophisticated our approach, strangely, the more we start returning to nature, the more it starts looking like something that didn't come from a computer at all. It looked like it came from under a tree. But that shows you some of the things that, some of the trends that are happening in technology now. We're seeing companies look into this for all kinds of things, from motorcycles onward, bicycles. And it's not just for mechanical needs, it's also for thermal needs. Because if you can 3D print a radiator, your improvements in thermal exchange are dramatically improved. So now we're seeing that as well. We're seeing the benefits of 3D printing extending in every direction. So add that to biomimicry, mass complex manufacturing. And here's a concept that Airbus had for the airplane of the future. Now, it's optimized and all this stuff. What it needs to make it happen is just a really, really big 3D printer. Because most 3D printers, they'll print about a cubic meter for the good industrial printers. Well, how do you break free of the box? That's one of the big challenges now. Well, a group that is near me where I live in Amsterdam is looking at 3D printing a canal bridge. But what's magical about what they're doing is that the robots, the repurposed industrial robots, actually climb the structure while they're 3D printing it underneath them. And that was a concept. I walked across the final bridge, which is now finished, 2 weeks ago, and it's an amazing bridge. What's important is not that Amsterdam has yet another bridge. We've got lots of them. But this says something about the change in architecture. When a printer can start climbing itself like a drone, climbing its own thing and building its own structures, that's a very different type of architecture. And there are a lot of people getting into the game. Drone printing. Dubai wants to print 25% of its houses in 12 years. Out of Berkeley, 3D printing, where each brick is 3D printed for its location, turning the house into a living organism and water filter. Or in this case, 3D printing a house in about 3 days for about $4,000. Now, the thing to remember when you're talking about 3D printing and architecture is there is no one solution yet. This is in its infancy. This is up for grabs. Anyone can take this and evolve it because nobody really knows what it's going to be like. This is a work in progress. Anyone want to guess where this structure is 3D printed? That's a concept, hasn't happened yet. It's a group out of London called Clouds Architecture, and they're looking at 3D printing on Mars. Now, Mars has what you need. It has your building material, ice, and it has a lot of it. All you need is that printer there that climbs around its own structure and 3D prints, in this case, an igloo. Now, ice gets you a lot of things. It's strong, it's plentiful, light gets through it, so you and Matt Damon can grow potatoes. And 3 meters of ice will block gamma rays. So when you or your children or your grandchildren or great-grandchildren, whoever goes up to Mars to live there isn't going to be irradiated because living in this igloo will protect them. Interesting enough. A little tangent on that front. My team at 3D Systems, we 3D printed this part. It's a rocket part, of course, but anyone want to guess what it's made of? It's a meteorite. Now, meteorites are very often nickel and iron, perfect building materials. So we ground it up, processed it, and printed a rocket part out of a meteorite. Well, that speaks to this idea that, of course, space has all kinds of good material in it. It's just that asteroids are traveling at 25 meters a second, 25 kilometers a second. So you have to catch them first. But once you do, you've got the ideal building material. So there are groups looking at 3D printing rockets in space. Now, the real sweet spot for 3D printing has been, and will be for a long time, is in medicine. And this makes a lot of sense because it speaks to all the sweet spots for 3D printing. The parts tend to be small. They tend to be exotic materials. They tend to be high user value. I mean, it's for your body, it's for your life. You're not going to cut costs there. High complexity, because nothing more complex than the body. Custom fabrication, because we're all different. Rapid turnaround time, all digital workflow, decentralized manufacturing. All these are dividends that contribute to why medical applications are ideal. Now, the thing to know, for one thing, is that medicine is a 3-day topic that we could just go on forever. It's a big, big topic now. But a couple takeaways. One is that there is no one machine that does much. All throughout the process, there are certain machines, different machines, used by different people with different skills, using different materials to deal different things with the data and come up with different outcomes. So it's widely varied what gets used in the 3D printing process in medicine. The 4 main categories I like to think of are preoperative planning, which is how to deal with the surgery before it starts happening, with perioperative guides, what happens once you're under the knife, osseointegration, things that get left inside the body, and then exoskeletal fixation, things like my arm brace. Well, When you take a couple of these, you take the first one, body-specific data visualization. The better the doctor has an understanding of what your body and what the condition is, the better the surgery is going to be. So in this case, multi-material printers can print a liver, and so that the doctor can hold that liver in their hand. Now, traditionally, they would have to take the data from CAT scans and such and imagine what that would look like in 3D, because CAT scans are two-dimensional slices. And they would have to reconstruct that in their head. Now they can actually hold it in their hand and see right through it. So this used to be crazy expensive. Now you can do this for about $90. So it's too cheap not to do for a surgical process. And it's not just that. You can print the parts before the surgery starts, and you can actually test drive with them, because you can hold that person's skull and spine right in your hand and make your strategy around that. And it's not just bones and organs. Stent placement, for example. If you're going to put a stent in somebody's brain or heart, you can test drive it first now. You 3D print that the artery, in this case the femoral artery going from your leg up to your heart, and you can practice test driving how you're going to place that stent as many times as you want before a human being is involved. It leads to greater accuracy, better outcomes, and again, it's the only way you can get there is with an all-digital workflow. The second phase, mass customization, body-specific design. Well, humans are really bad at accuracy. If a doctor had to drill every hole that you see there, put it in the perfect location, at the perfect angle, drilling it to the perfect depth, they wouldn't get anywhere close, because that's just too complex for a human. So instead, you 3D print it. The doctor simply sticks the drill in the hole and pushes. Anyone can be a very good doctor with that kind of condition. So for this, in this case, a spinal frame, where the accuracy is important, that makes all the difference. If there are any people who smoke, chew tobacco, or shoot things while you're drunk, don't raise your hands, but pay attention, because this is for you. That category of those three has surgeries specially designed just for you. So when the doctor discovers that you have a tumor in your jaw the size of a hamster, they will then invite you to the special surgery. What they do is they open up your face, they put you on the table, and they put you to sleep first. Sorry. Then they open up your face, and they bolt down these metal plates. Now they use those as guides, and they can make perfect precision cuts when they get rid of that big chunk of your jaw that you're not going to be using anymore. Now consider, this used to be a death sentence, because you can't function without a jaw unless you really, really like Jell-O. So this is all changing now. You actually have a second shot at it. So now they've resected the part of your jaw that you're not going to use anymore, and another doctor down at the other end of the table has taken out your second leg bone, your fibula. They've put it on the table. They've put down a cut guide. They've chopped up these little chunks, and they've put them in place, and they've bolted them down with a stainless steel or titanium frame that's going to stay in your body for the rest of your life. And then all you have to do is 3D print some teeth. It takes about 6 minutes to 3D print a tooth. Dentistry is all 3D printed now. And you're back in business. You'll be chewing crunchy food in a few months. So this is still exotic surgery. It's not available to everyone. It's not worldwide. So if this happens to you, take my number down and give me a call. Or probably better just text me or WhatsApp or something, because your jaw. I'll be like, what? I can't understand you. Did you just shoot a hole in your jaw? What's up? Have you been drinking? So now there are solutions to some of these very exotic, prohibitively deadly conditions because of 3D printing. The final one here, Osseointegration, which is the ability to make something that will stay in the body. So in this case, for example, hip cups. The bone wants to grow through a structure like this, a specific lattice. It's called a trabecular structure. So because you can 3D print any complex shape like this, you drop that hip cup in there and bolt it down, the bone will grow through it like vines on a trellis, and you have far less rejection rate. It'll actually integrate fully with the body. And it's not just hips and knees. It's everywhere from facial to skull to all throughout the body. So some of those prohibitively very damaging conditions now are dealt with simply by implants, and the implants will become a part of your body, fully integrated over time. And this is one of my favorite ones. This is a material called polycaprolactone. And what's interesting about this is that it addresses children's tracheas. So children who've had collapsed tracheas, they have tough time breathing, and they need a tracheal stent to hold the trachea open while they grow into it. Now, traditionally, what that meant is surgery, putting in metal plates or metal stents that hold the trachea open, and then adjusting, which is more surgery potentially, and then removing them, which is surgery again to pull out these metal chunks. But now, a doctor can have a 3D printer right there on their desk, design the part, print it out of this polycaprolactone, and put it in the body. Now here's the catch. It will be absorbed by the body over time, over a specific time. So as it's being used and as it's doing its job, it's also being digested by the body. And that by the time it has done its job and kept the trachea open, it's been completely absorbed and it's gone for good. So it's kind of like the cowboy riding off into the sunset, which is exactly what you want in medicine. It's less damaging for kids, it's less risk, better overall care. An alum of Singularity University, Dr. Julie Lin Wong, looked at 3D printing in medicine and said, wait a minute, this really works well in outer space. And that's her focus, is 3D printing in space for medical applications. So she started this company, 3D4MD. And then she teamed up with these guys, also from Singularity, called Made in Space. They have a 3D printer on the space station. And she and I teamed up with them, and we designed this finger splint based on a 3D scan of an astronaut. And it was printed in space. And you can see in the background there are the solar panels, and farther away is planet Earth. And so for long-term space travel or survival in space, that's a new opportunity. And it's not just space, it's places that are very far away, sometimes disaster areas, sometimes just remote locations. You can now 3D print your medical tools. Now, a company that I started a while ago was looking at scoliosis, curvature of a girl's spine. The problem is girls really don't like to wear that brace. So we decided, okay, it's a fashion problem, not a medical problem. So we designed a brace that would be ventilated, but also discreet, invisible under clothing, and also would look really good. So we let the girl choose the pattern because then she thought of it more as fashion than medicine. And I took this to the Louvre in Paris for a show they did, and women came up to me and asked, this is beautiful, can I get one? I thought, okay, this is strange. It's a medical product. Do you have scoliosis? And they said, no, how do I get it? I don't know. Nobody does. If you figure it out, let us all know. And we're looking at next generation braces that actually hold the girl into a correct position, but let her bend because it essentially becomes a spring. Now, you know how there are some companies, when they talk about them, they say, this was started by a guy and his son in a garage, and they use that kind of as a metaphor. This company was started by a guy and his son in a garage. They were looking at something called amniotic band syndrome, where kids are born but without fully formed hands. But the same applies to people who have lost fingers in industrial accidents or disease or who knows what. Well, now there's an app for that. You can simply go on their website, enabling the future, and the company's called Enable. Now, there's an odd sentence there you see, which is crowdsourced, peer-to-peer, philanthropic, distributed manufacturing. That series of words has never been combined before, because you can't. So, if a kid is born without a fully formed hand, what they need is a very expensive, very complex, very custom prosthetic hand. Well, that's very expensive, if it's even possible. But those are the sweet spots for 3D printing. And so these guys realized that. They came up with a website and an app where you can simply describe the hand digitally. It will then generate the geometry that then you can print on a consumer-level 3D printer. I designed this one. And kids can print hands now for other kids for almost no cost. In fact, no money is allowed to change hands, so to speak, because that's kind of part of the magic of what they're doing. It's philanthropic. And what we're finding out more and more is that kids with amniotic band syndrome are getting printers for themselves and then also printing hands for other kids. So it's becoming this really interesting philanthropic distributed manufacturing. And here's the hand that results. So suddenly a kid can put on their clothing, can eat, can open doors, can carry things, can do sports, can do things that would otherwise be very, very difficult without fingers and thumbs. It's a fairly primitive hand, but it is free. And it does get them from nothing to something. And it's only available through the digital design process. The next generations are going to probably be far more customized. They probably are going to have sensors in them, Arduino, Raspberry Pi, myoelectrics. And so we're going to see much more sophisticated hands, not for the hundreds of thousands of dollars that bionic hands have, but for very, very low cost, probably a few thousand, maybe down to a few $100 for a fully bionic hand. So that's revolutionary for a kid. Especially when you think that the entire technology, all of this stuff, only stems from one thing, which was the goal to create a dashboard faster. And that's why this is really a story about design and innovation, because everything that is not a dashboard is the product of somebody hacking the system. Somebody's taking this tool and exploring how something designed for one purpose might be totally repurposed for something different and might revolutionize an industry or invite you and challenge you to change something that had never been considered before. And so we're seeing that in every industry right now. We're seeing rockets go up faster and cheaper than ever before. We're seeing revolutions in medicine. We're seeing architectural changes and time to market happening. We're seeing startups far more competitive than the old behemoths, the old established corporations, because they're better able sometimes to take advantage of the new tools. Thank you.